Hello there. Trying to figure out how all this stuff works here, so if you give me feedback, I'd appreciate it. Maybe we'll do a little equilibrium free body diagram and see if we can solve for our reactions here. So here's a simply supported beam. Roller support on one end and hinge on the other. Put a couple of loads on here maybe. And some dimensions. Bring this over here so I can see better. So maybe this is maybe these are feet. So 1, 2, 3, 4, 5, 6, 7 foot here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 feet. Here, 1, 2, 3, 4, 5, 6 feet there. Drag those down a little bit. Alright, so now we'll do some equilibrium equations. So if we call this A over here, B over here, we can use our three equations. Sum of the force in the x direction is 0. Sum of the force in the y direction equals 0. Sum of the moments about any point has to also be 0. So if we draw a free body diagram of our beam, we're going to have, call this RA in the y direction. And we'll call this RA reaction at point A in the x direction. And then we've got reaction at point B in the y direction. And we've still got our 50 pounds here. And we got 100 pounds here. And we'll move our equations up out of the way so we can still see what's going on. So we'll start with the first equation. Sum of the forces in the x direction is 0, which equals RAX. Now that's pretty straightforward. So all we have is RAX, 0 pounds. So there's no x component of forces anywhere, so there's no reaction on that one direction. Alright, we could use the second equation, y equals sum of the force in the y direction equals 0, but we'll have two unknowns and only one equation. So let's skip over to the last one here. We'll sum the moments about some strategic point and see if we can't get that equal to 0. So I want to pick a point where the unknowns go through the point, because those forces won't cause a moment about that point, and that'll let me eliminate some of those unknowns. So if I sum the points about this edge over here, that'd be a good strategic move, I think, because RAX and RAY both go through that point, and so those unknowns will go away. So let's write the sum of the moments about the, we'll call that point right there, we'll call that the origin. Sum of the moments about O is 0, and we're going to draw a little triad here like we like to do to define the positive x direction, define the positive y direction, and we'll also define a positive moment as being counterclockwise. So if that's the case, then our moments are going to be 50 pounds times 7 foot, and that's a negative moment. So it's going to be negative 50 pounds times 7 foot. 100 pounds is also going in the negative direction. So I'm going to subtract 100 pounds times this moment arm, which is 10 foot plus 7 foot. Again, we're summing points, we're summing moments about that point A. And finally, my reaction to B is going up, and that's going to cause a positive moment. So I'll put that as a plus RBY times 7 foot plus 10 foot plus 6 foot. So now I've got one equation and one unknown, so my strategy is working out. And so 0 is going to equal to negative 350. I'll drop the units now because they're all foot-pounds, and so they're all going to cancel each other out. Just need to be consistent. So minus 350 minus 1700. 17 times 100, 1700. And then I'm going to add RBY times that moment arm, which is 23. And I can do some high school algebra. RBY, put these on the other side, it'll be plus 350 plus 1700. All of that divided by 23. And if I do some calculation here, I'll see what kind of answer I get. So I got 350 plus 1700. Divide that by 23. And I get something. It's off the screen. Looks like 89.13. So that's reaction at B in the vertical direction. Now I have one more equation, and I'll use my middle equation I haven't used yet. Sum of the force in the y direction equals 0. And I'm going to use the plus direction is going up. So I got RAY going up. I got 50 going down. These are all pounds. I'm not going to write down the units, but I know they're all pounds. I'm being consistent. And I got a minus 100 pounds. And then I got a plus RBY, but I already know RBY. And so now I've got one equation and one unknown. And again, doing some algebra. So I'll make this a plus to minus here somewhere. Thought I had a button for going plus to minus. There it is right there. So I got negative 89. On the other side, I'll add 50. And I'll add 100. And I get 60.87 pounds. So that's my equilibrium equation. So now I've got my three solutions. I'll highlight those in green. RAX is 0. RBY is 89 pounds. And RAY is about 61 pounds. So that looks like a engineering 3375 type problem. And also maybe a 3311 problem. So got a request to do composites. All right, so that's a good topic. So we're talking about doing some kind of a stress analysis on composites, or doing some hand calculations. What kind of composite problem you want to try to solve? We can do simulation problems in composites with SolidWorks. I think the advanced module has that capability. Let's turn off this beautiful little thing going here. So this is a little thermoelectric cooler assembly that we did some thermal analysis on. So somebody wants to see some of that stuff, we can do that in the future. So let me start a new thing here and see what kind of options we have under SolidWorks simulation, if that's what you're talking about wanting to do. I don't want to open, I just want to do We'll open up some empty part here. So the first thing you'll do is need to get SOLIDWORKS education version. If you're a student, you can get that through the classwork. Okay, yeah, stress analysis. So that's right up my alley here. So let's see what we got here. You've got to go SOLIDWORKS. You got to go Tools, and we got to look at these add-ins and see what kind of modules we have available. And so you'll want to do the same thing on your computer. So we've got SOLIDWORKS simulation. So let's turn that on. So I just went to Tools and then went to Add-ins. And if I turn on these modules, they'll load inside of SOLIDWORKS. By default, they don't load automatically. There's a ton of them. If they loaded all of them all the time, then it would take forever to open up SOLIDWORKS. So once that's added, then we should, it's got a little waiting hourglass here. We'll wait and see if this thing loads up. We should be able to see what kind of modules. I know that, I don't know if that was, you were part of that team, but I know one of my students went to a conference back before all this COVID hit, and they were building some composite structures to build a bridge truss, basically. And they were trying to, I'm not sure exactly all the details, but they were trying to design and fabricate a composite material truss to handle the most weight it could. And I don't think they ended up going. I think they just shipped their entry to the contest and they hung the weights on there till it failed. And I'm not sure, I'd encourage them to try to do an analysis to try to see how their design worked before they built it. And so if you're familiar with that conference I'm talking about, I can put you in touch with that student that went and give you some more details. So once the modules are loaded, we can make sure the simulation is turned on. Flow simulation, we should get another tab up here somewhere. Flow simulation, here we go. So we want this structural simulation turned on. Once we get that tab, well, this thing is running slow. Still thinking. So SOLIDWORKS flow simulation already had loaded. And we'll get my keyboard down here so I can see what I'm doing. So it's busy. So under simulation, the one I've used, some of the classes I've taught are the fatigue module. You can do fatigue stress, find out if your system's going to fail due to fatigue failure. They have a buckling simulation, and I'm pretty sure they have a composite simulation module. And what it allows you to do for the structural analysis for things like I-beams and aluminum channels and things, that material is isotropic. And so like this heat sink, the strength of the material is the same in all directions. So that's isotropic. For things like wood, it's not isotropic, so you can't use the same modeling techniques. You can use the same modeling techniques, but you need a different solver to be able to handle the different structural component material properties in different directions. And composite, as you know, is definitely anisotropic. It has different material properties in different directions. And what this module allows you to do is define those material properties. And it also allows you not only to define them in X and Y and Z, but it also lets you align or define those material properties for different layers of composite material. So if you've got fiberglass weave that you're making an epoxy composite material out of, you might run your glass fibers, say, in the 0 degree direction, and then you might lay up the next layer at 90 degrees, and then the next layer at 45, and the other layer at minus 45, and do those alternating layer stack ups. You can define your material, you can define those thicknesses and those anisotropic materials in each layer, and so each layer has its own direction where the strength, it's going to be stronger, obviously, along the glass fiber direction or whatever your reinforcement material is, whether it's nanotubes or fiberglass or glass fibers, whatever they are. You can define that stack up, so it's much more complicated to define the material, but once you define it, you can run this different module, and it's got a different set of equations because the regular structural analysis tool just assumes isotropic material, so the strength's the same in all directions. And if you got a composite material, you've got to take that into account. So here's a simulation tab, finally loaded. So if I go get a new study, let's see what is available here. So we've got thermal buckling. Nonlinear might be what we're looking for. So I think the answer to your question is, yeah, we could do some composite analysis. So here's what I'll ask of my person to ask the question. I don't know if y'all can all see the chat window or not, but send me a problem you'd like to look at, and start off with something simple so that we can do what you want to do when you do these analysis simulation. You want to start with something simple. You want to do an analysis on a part where you can do hand calculations to calculate the stresses in your part using traditional engineering hand calculation method. And then you build a model, you run the model, and if those don't match, then you've got a problem with your model. You want to make sure that the model matches the hand calculations, and then, ideally, you take your test specimen of whatever the sample product is, you take it downstairs to Dr. Tate's lab, put it on the MTS machine and pull it until it breaks, come up with a real answer. That's the real answer. Nature, it does what it does, and if your hand calculations and or your SOLIDWORKS simulation don't match that, you need to go fix your hand calculation, go fix your model. Then once you get that to match, then you have high confidence in your model, and then you can do things like making more advanced shapes that you may or may not be able to actually test, and you have high confidence in your model. So anyway, bottom line, send me an example. You got my email address. Send me an example of what you'd like to see, something simple, and give me some materials, and I'll build a model and make a video and put that on the agenda. So good idea. Thank you. Any other ideas for future topics? I'm kind of doing this, kind of kick this thing off, see if I can get any interest. And if so, we'll just keep doing it until interest goes away. You bet, Abigail. Good to see you. Good to hear from you. So yeah, send me an example, and I'll put something together and see what we can come up with. We've also got Ansys Workbench that I know has nonlinear, non-isotropic material capabilities. So I'm not as familiar with Ansys Workbench, but it is available in the department here, so we could investigate that too and see, give us another tool to use to do some composite modeling. A little test specimen here and see if we can't see what that nonlinear module looks like. Okay, let's go simulation. Now, where are these dimmed out here? May need to close SolidWorks and start it back up again. Let's save this as something. When you load those modules, sometimes it gets confused. So let's save this and close it and open SolidWorks back up. Plus that'll give me the chance to close these other models out. So anyway, some of the stuff I pulled up here before we started, try to get some ideas going. So it's an empty one. That's not very interesting. Wow, this thing is really crawling. A YouTube thing. Taking a lot of bandwidth here. So I was going to show you, I've got a little CAD model of a waveguide that we can learn how to do configurations inside of SolidWorks. So if you haven't done configurations, it's pretty interesting. There's that heatsink thermal cooler assembly. And somewhere I've got a drawing of this waveguide so we can learn how to do drawings. We're doing that in engineering graphics course at ACC and here at Texas State. So we can learn how to do that, and also the modeling, SolidWorks modeling. We can do assemblies and part configurations. And so let's close out all this stuff. See if I can relaunch SolidWorks and see if it doesn't give me that module so we can take a look at that. What I might need to do also in the future is, since this thing is running so slow, is to do some pre-recorded videos, and that way you can watch those on your own time and not have to wait for SolidWorks to load. So maybe I'll do that with a composite problem, do something and then post it on my YouTube channel so y'all can watch it between now and the next episode, and then we can discuss it in detail. So here are those add-ins it's loading. It takes, depending on how many I'm going to load, it adds quite a bit of time to the load time, but see if it doesn't load that premium simulation, and then allow us to get to that module to see what kind of options we have for the different anisotropic materials. All right. So let's open up this little guy. see if that module didn't work this time. Okay, so if we go turn on the simulation tab, and we should get a, man, this thing is just painfully slow. Got an hourglass popped up. I gotta get this fixed. This is taking too long. I have to turn off my little webcam. I think that's driving up the CPU time here. Yeah, that's my video capture. Maybe I'll turn that off here in a minute. All right, looks like we're back. So if we go simulation, and I want to turn off this video feed thing, so you don't get to see my pretty face, but maybe we can do this quicker. Okay, well, maybe that'll be, that's all the questions I've got so far. So what we'll do is I'll come up with a little composite problem to work on, get some feedback from a commenter that had a good idea, and we'll see if we can get that nonlinear module to work, and if not, we'll try, maybe we'll run it in Ansys. So anyway, thanks for watching. Sorry for the slow speed. Part of my idea today is to test this thing out and see what I need to tweak to make this thing more appealing for folks to take time out of their busy day to visit. So anyway, subscribe, hit the subscribe button on the YouTube channel so you'll be notified. We're going to try to do this again on Wednesday evening. So try to do these on Wednesdays and Sundays every week. So anyway, thanks for stopping by, and hope to see you at the next one.